A single mistake accompanied by a system malfunction caused one of the deadliest MD-82 accidents in its service history. The McDonnell Douglas MD-82, nicknamed Mad Dog, is a narrow-body twin-engine jet airliner with a maximum passenger capacity of 175. On the 20th of August 2008, Destiny had its own plans with 172 souls on board. Hi, my name is Thomas from Air Distress. I demonstrate best possible what happened on Spanair flight JK5022 servicing Madrid Barajas to Las Palmas, Gran Canaria. Everything shown is based on facts provided by the final accident report. If you like my work, please subscribe and like the videos. This is the support needed and is crucial to keep these videos coming. Thank you. It all started in the morning of the 20th of August at 0800 local time when the crew arrived at the Barcelona airport in the operator's office. A short pre-flight briefing was held before preparation of the aircraft began. At 0855, the McDonnell Douglas MD-82 tail number Echo Charlie Hotel Fox Papa took off from Barcelona to Madrid. At 10:13, the MD-82 landed in Madrid. Nothing special so far. There was no entry made in the aircraft's technical logbook ATLB. Echo Charlie Hotel Fox Papa was scheduled for 1300 same day and same crew as on the previous leg with call sign JK5022 for the flight from Madrid Lima Echo Mike Delta to Gran Canaria Golf Charlie Lima Papa. The Great Circle distance, which is the shortest air distance between these two airports, is around 950 nautical miles or 1,759 kilometers. At 13:06, the crew contacted clearance departure east on 130.080 to request pushback and startup. At 13:10, the Mad Dog MD-82 was pushed back at stand Tango 21. After starting the two Pratt & Whitney JT8D-219 engines, they requested taxi clearance with south control on 121.855 and headed for runway 36 left via taxiway Mike to Romeo 1. The MD-82 was now fully ready and configured with flaps set to 11 degrees.
Spanair 5022 approaching Romeo 1, ready for departure. Spanair 5022, wind 150 degrees 6 knots, cleared for lineup and takeoff runway 36 left.
Some seconds later and before the commencement of the takeoff roll, the crew transmitted the following message to Madrid Tower.
Madrid, Spanair 5022, look, we have a slight problem, we have to exit the runway again.
The story of Spanair 5022 was taking from now on another than normal direction. The crew had spotted an abnormal high RAM air temperature RAT. The flight data recorded indicated 56 degrees Celsius at the time of commencing the taxi, while it continuously rose up to 104 degrees Celsius. The RAM air temperature RAT, also known as total air temperature TAT, is the temperature of the air sensed by the aircraft's RAT probe up in the front of the aircraft. This value is normally higher than the ambient, or in other words the static air temperature SAT, due to the effect of the air's compression and the resulting heat from it as the aircraft moves at high speed through the air. The total air temperature is the sum of the static air temperature and the kinetic component called the RAM rise. On the ground while taxiing, the RAM air temperature is equal to the ambient air temperature since the speed is yet too slow for any heat rise. The RAM air temperature is forwarded to the aircraft's air data computers to convert the value into a static air temperature SAT required as a crucial input to calculate the true airspeed, for instance Mach number, engine parameters and other highly important and required figures. After contacting the Spanair Maintenance Control Center, the captain was told to reset circuit breaker C29 several times, which the captain had already done. Pulling the circuit breaker C29, located in the lower panel behind the left-hand seat, cuts the electric power to heat the RAM air temperature probe. The ram air temperature probe, as well as other probes, are prone to icing and are therefore heated. For some systems, this is the case already on the ground, but the ram air temperature probe heating should be inhibited on the ground. This is achieved by an electromechanical relay R2-5, which receives information from the air-ground switches installed on the gear. If the aircraft sends ground mode, the heating of the ram air temperature probe should be inhibited, but as soon as the air-ground switches send air mode signal, the RAD probe heating turns on. A heating of the probe on the ground due to a system malfunction can cause an extensive ram air temperature indication. Why the famous R2 relay plays a crucial factor in the outcome of flight JK5022, I will answer in depth at the later stage. As an additional fact, and according to the flight data recorder readouts, Echo Charlie Hotel Fox Papa had between the 18th and the 20th of August 2008 several issues with high ram air temperature indications. Except for this flight, on all other occasions a takeoff was commenced with a high ram air temperature reading. Let's quickly have a look at the flight data readout script. In the evening of the 18th of August 2008, the data recorder showed a high ram air temperature of 40 degrees Celsius prior takeoff. The aircraft took off with the high ram air temperature and no entry was made into the aircraft's technical logbook. Same happened several times during the day of the 19th of August 2008, so literally the day before the fatal accident. While the ram air temperatures read 100, 50, 100 and 90 degrees Celsius, on all occasions the readings were spotted before takeoff. It certainly shows that there was definitely an issue with the system that could or was obviously not resolved. Due to the inability to solve the problem on the day of the accident flight by simply resetting the circuit breaker C29, the aircraft returned to stand Romeo 11, at which it arrived approximately around 13:42. The crew requested maintenance service at the stand to further investigate the problem. At this point, it was approved by the Spanair headquarters in Palma de Mallorca to replace the aircraft as another MD-82 was available. The crew, however, decided to wait until maintenance would have a look at the malfunction. The maintenance technicians did a variety of tests, confirmed the heating of the probe by mistake, but couldn't solve the problem itself. According to the minimum equipment list MEL Ice and Rain Protection 30.8, the technicians saw that the aircraft could still be dispatched with the probe heat inoperative, in this case by leaving the circuit breaker C29 pulled and therefore cut the electric power to heat the probe as long as the aircraft would not enter icy condition. Now let's have a look at the corresponding Spanair MEL section. Here you see on the left side section 1 under 30.8 the system involved. The letter C in section 2 simply defines in which period of time the root cause of the problem needs to be fixed before the aircraft will be grounded. In this case the letter C stands for 10 days starting at midnight of the day of entry. However, pulling the breaker C29 cuts not only the power to the probe heaters but also to the thrust rating panel, which is required for the auto throttle system to work. This further means that the crew would have to set engine power themselves throughout the flight. Section 3 shows that the MD-82 only has one RAD probe heater, while Section 4 tells us how many of the installed systems need to work prior to dispatch, so in this case none, but under which conditions is defined in Section 5. As mentioned earlier, it is only approved if flights are not made in known or forecasted icing conditions and a placard was installed. The proposal to dispatch the aircraft under the requirements of the MEL was forwarded to the captain and he agreed. Now an inoperative label was placed over the RAD display, the issue documented and deferred to the aircraft's technical logbook and the corresponding hold item list in accordance with the minimum equipment list as a category C item. The aircraft was thereafter released to service. It is obvious, by not making an entry in the aircraft's technical logbook, like on the days before with the existing RAD malfunction, It does not activate the 10 days period to solve the problem. However, such a behavior is questionable and makes the aircraft certainly not safer. At 14:02, the crew decided to compensate the consumed fuel amount up to this point by refueling. At 14:07, the first officer requested permission to start engines, which they received shortly thereafter at 14:09. During the startup process, the crew discussed the need for taking off without the auto throttle system since it would not work due to the pulled C29 circuit breaker and therefore disabling the thrust rating panel TRP. While they were doing the after start check and right at the point 9 flap slats, the commander asked the first officer to ask ATC for taxi clearance. Therefore point 9 was omitted. The flap and slat check is one of the crucial aircraft configuration checks prior takeoff, which should verify the correct settings on the lift devices and indications shown on the flap and slat indicator on the central cockpit panel. There are 4 lights in the vision of both pilots indicating takeoff, disagree, auto, and land. The takeoff light should illuminate when the flaps and slats are set in the takeoff range. If the flap lever is moved to whatever takeoff setting, the slats should move automatically to a predefined position. The amber disagree light indicates that the left and the right slap positions do not agree with each other and/or with the handle position. The auto light, the third from the top, indicates the pilots that the slap positions have changed automatically from a mid to a fully extended position by the stall warning system. This means that if the aircraft stall warning system senses a stall or near to stall situation while the slats are not fully extended, the system would trigger the slats automatically to the extended position to increase the lift capability of the wing. The last light in the row is the slat's land advisory light. It indicates the proper slat setting during landing configurations. Each section is equipped with 2 light bulbs to increase redundancy in case a light bulb should fail. If the aircraft is properly configured for takeoff, the blue takeoff light should be illuminated. During the accident investigation process, the slat advisory light panel light bulbs were sent to the laboratory of National Institute of Aerospace Technology INTA for analysis. It was determined that the takeoff lights were off but fully operational at the time of the impact, meaning that the slats were physically not in the takeoff position. Beside this process, the central pedestal was recovered from the aircraft's wreckage. It showed massive impact damages. The flap slack control lever as well as the fixed track were removed from the pedestal and sent also to the INTA for further analysis. Based on the signs of the marks, damages and deformations, it was believed that the flap slack control lever was in the up retract position at the time of the impact. The outcome of this investigation confirmed the data from the flight data recorder on which the flaps were shown up at all times and further reveals that the aircraft was therefore in an incorrect fatal takeoff configuration at the time of the impact. Obviously, a major mistake was overseen by the crew during the takeoff checks that contributed to the fatal outcome of this accident. As per the nature of humans, we all make mistakes. Therefore, and especially in aviation, there have been and will always be systems in place that should keep us away from doing such fatal mistakes. That is why I highlight the word contributing factors. Yes, there was a major mistake overseen, but as we all know, an accident happens mostly due to a series of mistakes formed as a chain. In this particular case, there was another system not working the way it should have. But let's first continue with the reminder of the flight before I raise the finger on another crucial system that has failed. While the crew waited for the taxi clearance, they calculated the takeoff EPR, the engine pressure ratio, or in other words, the power setting required for takeoff. This value was correctly defined to be 1.95 and would have to be set manually due to the absence of the autothrust system as previously discussed. A moment later, JK 5022 headed for the second time this day to the holding point runway 36 left. From the start of the taxi sequence until the end of the recordings, the flaps and slats deflection readings indicated 0, which is obviously the wrong setting for normal takeoffs. Meanwhile, Mad Dog MD-82 contacted departure frequency for runway 36 left to let them know that they reached taxiway Romeo 5, which is shortly before the final holding point runway 36 left.
Spanair 5022 next in line behind airline MD-80, taxi into position and hold runway 36 left.
The crew read back to clearance and therefore expected the takeoff clearance without delay. At 14:22, two chimes were heard on the cockpit voice recorder used by the chief flight attendant to indicate the pilots that the passenger cabin is ready for takeoff. Now it was time for the crew to perform a takeoff imminent checklist. The first officer read the items which the commander verified. This checklist included the following items: cabin alerted, ignition set, spoiler and ABS auto braking system armed, brake pressure and temperature checked, windows closed, and final items. The last point on this checklist calls for final items. The Spanair operational manual did not specify what exactly is included and defined under this point. The investigation included also interviews with company pilots about what had to be done. They agreed that this item had to be spoken out loud by the first officer from memory without the need of the captain to reply. However, the captain had to supervise the first officer, ensuring that the points mentioned by the first officer correspond to the actual condition of the systems. The parameters and settings for takeoff critical components are checked, including the flap and slat indicator. Here it was given away another chance to spot the wrong configuration shortly before takeoff. At 14:23, so literally 1 hour after the first takeoff attempt, Spanair 5022 received the takeoff clearance for the second time.
Spanair 5022, wind 21005, cleared for takeoff, runway 36 left. Cleared 36 left, Spanair 5022.
Now the fully functioning Pratt & Whitney JT8D engine spooled up and the brakes were released. The MD-82 was screaming down the runway while the crew was manually adjusting the takeoff power to EPR 1.95.
60, 100, P1, power check, rotate.
Throughout the takeoff run and until the end of the CVR recording, no takeoff warning sounds from the takeoff warning system were recorded, which would have alerted the crew about the wrong takeoff configuration. Later investigations confirmed the speakers in the cockpit were fully functional. Shortly after liftoff, the stall warning and stick shaker activated, as well as a synthetic voice warning the crew about an aerodynamic stall. The first officer was not quite sure what was going on and raised the question whether they had an engine failure. At this time, the aircraft was at about an altitude of 25 feet above the ground, with a pitch angle of 15.5 degrees nose up and a right bank angle of 4.4 degrees. The pitch angle further increased to a maximum of 18 degrees, while the aircraft reached a maximum altitude above the ground of 40 feet and a bank angle of 20 degrees to the right. Throughout this scenario, the throttle angles were changed in an unsymmetric way towards a reduced power setting. The left throttle by 4 degrees, the right throttle lever by 32 degrees. As a consequence, the power dropped from takeoff power to a value of 1.65, which could be seen as a fatal move. A moment later, the power levers were slammed to the full forward stop end, and while the engine reached a power setting of 2.2 EPR, these values remained unchanged for the rest of the flight. Now the bank angle warning triggered by the Enhanced Ground Proximity Warning System EGPWS was heard on the cockpit voice recorder together with the stall warning. However, the crew did not identify the stall and therefore did not initiate an after takeoff stall procedure. The stick shaker remained active until the first impact at 14:24 and 24 seconds at the speed of 154 knots. The aircraft crashed to the right of runway 36 left and was completely destroyed as a result of the impact and the post-fire. From the 172 souls on board, 154 died, 18 survived with serious injuries. Now it's time to go back to the earlier mentioned and crucial system that has obviously failed. The MD-82 was equipped with a so-called takeoff warning system. Why in the world did the takeoff warning system not work on the accident flight? The takeoff warning system should have alerted the crew about the wrong flap and slack configuration once the thrust levers were pushed through 33 degrees of its travel range into the takeoff position. But as the cockpit voice recorder proved, it remained silent. Let's listen to warnings that are generated by a properly working takeoff warning system on an MD-82. This is the rather famous R2-5 relay named by the position on the circuit breaker panel that caused many headaches in the past already, not only on the accident model MD-82. The relay is part of the air and ground mode, ram air temperature probe heating, but also plays a role in the takeoff warning system power distribution. It is basically an electromechanical switch which opens and closes electrical circuits. Even though the high ram air temperature experienced in the beginning of the flight had nothing to do with the accident itself, there could still have been a correlation between the faults experienced with the takeoff warning system and the probe heating. This would especially count for a mechanical failure on the relay contacts, the pivoting armature, or a problem with the copper coils. As you can see on this diagram, the relay R2-5 has 4 sections divided into A, B, C and D. Special focus during the investigation was set to section B and C of the contacts as they are responsible for the takeoff warning system B and the ram air temperature probe heating C. To exclude the possibility of a not working takeoff warning system due to a pulled circuit breaker C29, the investigation team tested this scenario physically on other MD-82s. However, it was confirmed that there is no correlation between the circuit breaker C29 and the takeoff warning system. The R2-5 relay was inspected to determine if it could have failed. The initial analysis in June 2009 included a borescope inspection and a radiographic test beside a continuity and functional test with and without a thermal chamber. The delay was within specification for the first test at ambient temperature and with the coil de-energized and energized. However, an abnormal behavior was detected when the relay was kept energized while the relay temperature rose to about 57 degrees Celsius, whereas a new relay never got warmer than 40 degrees Celsius. In that particular situation, contact 1 and 2 of section C, which should be closed when power is applied, separated when the relay became hot. The material on contact C2 and C3, which are in the line of the ram air temperature probe heat circuit, show clear deposits. It could not be concluded from the tests whether this behavior was the root cause for the initial high ram air temperature or whether it came from the damage suffered in the accident. All the other sections relevant for the takeoff warning system and the air-ground system functioned normally. After all the tests carried out on the relay, there were no obvious and straightforward reasons which would have given evidence why the takeoff warning system did not work. However, it was not the first accident in aviation history similar to this one where a wrong takeoff configuration led to fatalities while the takeoff warning system remained silent. Therefore, one could think that the takeoff warning system was by design not the most reliable one. On the 16th of August 1987, a MD-82 from the Northwest airline, so identical to this aircraft type, crashed after takeoff at Detroit Airport due to an incorrect flap and slat setting. The takeoff warning system did also not work. A total of 156 people died. During the investigation, Douglas Aircraft Company issued an alert note to all DC-9 operators, which also included Spanair, with the recommendation to include takeoff warning system check prior each takeoff. On the 5th of June 2007, a MD-83 took off from runway 03 at Lanzarote Airport. Shortly thereafter, the aircraft entered a stall and almost crashed due to a wrong flap and slat setting and a not working takeoff warning system. There were also similar high RAM air temperature incidences within the company of Spanair. One is really interesting and shows a correlation between a high RAM air temperature and a not working takeoff warning system. On the 2nd of July 2009, so literally 1 year after the tragic accident, a MD-87 crew spotted a high RAM air temperature while taxiing. Upon noticing the situation and remembering the similarity with the previous accident within the company, the crew decided to perform a new takeoff warning system functional test, which failed. The maintenance facility did troubleshoots on the system but couldn't replicate the fault. In this particular situation, the maintenance manual instructed to replace the R2-5 relay, which they did. There were no further high RAM air temperature indications on that aircraft ever again. The list will continue with similar to identical accidents or incidents. One thing they had all in common: the checklists were not executed properly while the takeoff warning systems were not working as per design, and often together with a RAM air temperature indication malfunction. Now it's time to summarize the most important findings and causes. The opening of the circuit breaker C29 interrupted the power to the RAM air temperature probe heater and the thrust rating panel, but had no influence on the takeoff warning system. The pilots used the Spanair checklists but did not fully execute or complete them. The flap and slats have not been set and later not verified in the correct position. The checklist posed several opportunities to spot this fatal mistake. The takeoff warning system did not issue any takeoff configuration warnings during the takeoff. The Spanair checklist did not include a takeoff warning system check for each and every flight, but only for the first flight of the day. In 71 of 103 high RAM air temperature indication incidents reported from DC-9-AD series operators, the changing of the R2-5 relay solved all the problems. The aircraft entered the stall after liftoff while the stick shaker was activated together with aural bank angle and stall audible warnings. The stall was not identified by the crew and therefore no countermeasures were taken. The crew misinterpreted the situation and the first officer believed an engine failure to have happened. He momentarily retarded the throttle levers.